Hello! Today I want to show you how to create contracts for VSC. They're written in TypeScript, and the only things that you need are the node repository for deploying and calling the contract, and an installation of IPFS and MongoDB. To get started, we want to start up MongoDB and IPFS and open VS Code. Here we want to create the files we are going to use to create our contract. A contract in VSC from the code side consists of its actual code and a manifest. And as we, for the first example, are going to create something that in really simple terms resembles an NFT contract, we are going to name it nft.ts for the contract code and nft.manifest.json for the associated manifest. The manifest looks like this. We got a name of the contract and we got a description. This metadata needs to be set for every contract. But before we dive in, let's just think about what we really need in terms of components if we want to build something that vaguely resembles an NFT contract. So we need some kind of registry to store or map the ownership to the data. We need some kind of arbitrary data that we want to basically wrap in the NFT. And we need interaction logic. For example, adding more owners to the NFT, minting the NFT, and so on. We should also go over what the VSC Smart Contract API has to offer us. For that, I prepared the small code snippet. And here I can basically explain the basic building blocks that you will need for building smart contracts. The concept behind those actions is that this here in the back signifies the method name, which in this case is basically called init. For the rest of the concepts we got here, we got for once the storage API, which basically gives us access to a key value store where we can store any arbitrary data. And it works like you would expect it to. You have a key and a value, and you store a value under key name, of course. For example, here we have a key that's called anyKeyName. We store an object with a message that's called hello world in here. And here we basically pull this key. So in this variable, we should get the value that we supplied here. So the object with the property message and hello world. We also have information in regards to the environment. For example, we can also retrieve the ID of the sender, so basically the person that invoked the contract. And we can also get information about which block this transaction is included in. And to further elaborate on the concept of the storage, I prepared another snippet which should show you how you can basically create nested structures inside of the key name in order to basically store the data in a syntax that's like level DB. You will see what I mean in this practical example. Here we have a key name that's called NFT/first NFT. Here we have a similar key name that has the name NFT/second NFT, and in those we store some arbitrary data. And now with the state.ls command, we can retrieve every object that's behind this first key, this first level basically. So in this object, we should get the value of first NFT and second NFT. So that should be it for the basic building blocks that you need to create a contract on VSC. One important thing I still want to mention is that we obviously have some limitations and constraints on the classes that you can use inside of the contract. For example, it is currently not possible to use regex and math.random. This one is an obvious one, as smart contracts need to be deterministic throughout the different node executions. It is also not possible to use JavaScript's setInterval and setTimeout. Those would make the functionality of a contract unpredictable as well. But don't worry. If you still need some random values, you can rely on other sources that you can harvest for those sweet pseudo-random numbers. This code, for example, uses the included block hash to get a random value inside of the contract. This should be sufficient for the majority of simple applications. And as time progresses, the Smart Contracts SDK will be extended with more and more features that will aid you on your coding journey. So you'll fight less of these problems on your own. But now enough talk. Let's get started on our example. For that we will start with something that you should always have in an NFT contract, a mint function. And here we are already doing something weird. Why get the last ID from the latest NFT? The reason for that is that we are going to use an incremental number for the NFT ID, which we would have to, if we would decide to not explicitly save it, need to search for in the whole array of potential NFTs. In other words, we would have to find the max value and therefore iterate through every NFT to find it, and as we aim to optimize contracts for minimal database calls and efficient computing, we can better lay off some responsibilities to this variable. As we have now obtained an ID by incrementing the latest one, we can now update its data and owner record. For the last part of our simple mint function, we will update the last ID variable for the just named reasons. And that should be it for our simple mint function. Let's move on and implement something that is fairly easy to implement as well, a duplication function. So, we start by fetching the array of our NFT owners that we specify via parameters into a variable. For the next step, we check if the sender of the transaction is listed as an owner of the NFT to only allow the owners to duplicate their NFT. Now we simply add the owner to the state and update its value. Alright, that should be it for a simple duplication function as well. Obviously, this is just a rudimentary example. In a real-world scenario, you would implement lots of verifications and checks to prevent misusage. And you would also probably implement functions that are responsible for burning the NFT or transferring it. But we will not do that now. Though what we are going to do now is finally deploying our contract. In order to deploy our contract, it first needs to be compiled to plain JavaScript. This can be done by running the npm command npm run contracts compile. Okay, that should be it. Great. Now we just need to push it on chain. For that we use npm run contracts deploy. Perfect. Here we got our contract ID. We need to remember this one, as we now want to interact with the contract and invoke one of the newly created methods. We can execute the methods via the call contract script that resides in the source/transactions directory. So this one here. So here you can see how we have to parameterize the script in order to call our contract. So let's just do exactly that. I'm going to open up an editor window so I can more easily construct the command. For the first parameter, we will paste in our contract ID. So this one here. For the second parameter, we want to select the method that we want to execute. So in our case, let's just try to mint an NFT. And for the third parameter, we decided on that we want to supply an NFT name and a record manifest. Currently, we have to construct the parameter object manually and need to parse it into a proper format so the CLI can read it. This means that the JSON string that represents the object must not contain any spaces and all parentheses are escaped. I already prepared an example JSON basically, but as you can see the parentheses are not escaped yet, but I on purpose left out all the spaces on this string here. But instead of manually escaping all the parentheses, I use a website like this where I just plug in my object, press escape JSON, and then I can copy off the value and plug it into my parameter. Alright, the moment we've all been waiting for. Now we're going to call our contract. I'm just going to copy the prompt we've just created and execute it in the root of the VSC project. And here we go. We received our transaction ID here. We can now use the ID to check the current state of the transaction. This can be done by querying the GraphQL endpoint of a public VSC node. I linked the one I'll be using in the description. You can also find the queries I will be using in there. So this is now the query which searches for the transactions and gives me the following properties. A transaction may be in 3 states. The first state is that a transaction is unconfirmed. This means that the transaction is broadcasted but not included into a block yet. After a little while, we switch to the second state, included. Like the name suggests, the transaction is now included in a block. For the final state, we have confirmed. This means that the transaction has now officially been processed by the network. And there we have it. We have now created and invoked the contract on VSC. Thank you for your attention and interest in the project.